we've done so far discontinuities in the form of vertical asymptotes and holes. We've also looked at horizontal asymptotes. Okay, so we have vertical asymptotes and holes for discontinuities, horizontal and slant asymptotes for end behavior. We're going to look at today are intercepts. Okay, intercepts. What are intercepts again? Simply put?
Where the line or whatever the thing is crosses the axis.
Yeah, where the curve or line or whatever it is crosses the axes. Okay, X and Y. How do you find the x-intercept? Anytime. Set y equal to 0, the function equal to 0. How do you find the y-intercept? Alright, so this is not a difficult lesson at all. But we're going to pick up on trends. That's the important part. Is that clear? And now you know how to do this. You've done it already. Let's pick up on trends. Look at number 1. Read through it on your own. Take about a minute. I want someone to explain the simple trend you could always look at. If I don't explain this one, what's the simple thing you can do? Pick up on it. If you have a rational function, if you want the y-intercept, just look at what? Look at what? Yeah, so what are those called? Just the word for numbers without x in a function. What is it? Constants. So it's really just the ratio of the constants. Think about it. We've done one already where to find the horizontal asymptote, we looked at the ratio of the leading coefficients when the degree of the numerator equals the degree of the denominator. Now, for the y-intercept, just always look at the ratio of the constants. That's it. It will always work. Because clearly these become 0, right? It's not a really difficult thing to do. You can just keep saying set x equal to 0, but just to make it easier on yourself, look at the ratio of the constants. Okay? Look at number 2. Read through number 2. Ryan, read it out loud actually for us. Then we'll go. So the answer is obviously, but how is this related to y-intercepts? How is this related to y-intercepts?
Since it's initial, it's like how much you started with, so that'll be your time will be 0.
Yeah, start getting used to this concept. When time is 0, it means the beginning of a physics problem or economics problem or some time-based problem. When time is 0. When time is 0, time is like x. Time is always going to appear along the horizontal axis. I may have seen once or twice in my life in all engineering where time is on the y-axis. Time is always going to be your independent variable. Why? Why?
It always changes.
Time always elapses. Always elapses. It's not going to be like you want time on the y-axis, like, well, let's figure out the time. No, time always elapses in some predictable fashion. Every second after another counts. Like, I mean, we can start getting into questions of what is time, right? It's ridiculous to think about. I mean, really, what is the second defined as? Do you know what a second is actually defined as? Anyone know? It has to do with the time it takes part of an atom to move, to be excited from one state to another. It had to do with there's a universal constant they use to measure a second. Well, in these cases, time we count up no matter what. What can we not have usually? What do we not usually talk about when it comes to time. Negative time. So graphs with time are usually in what quadrant? Look at your quadrants.
The first,
First and
third,
could have fourth. Why fourth? You could have a negative y value, right? Look, it's a stock value. In this case, the lowest you can get is 0 for this case. But you could clearly have a negative value on the y-axis. What's an example of where you have a negative value? Maybe it's the amount you have in the bank. You got your savings, ton of money in your savings. And the stocks take a drop, and you spend a lot of money, and now you're in debt. You want money in the bank. You'd be in the negative region. And maybe you go back to the positive. So you could have negative and positive y, but usually with time, there's only a positive in that value along the horizontal axis. So in this case, we're trying to find the initial stock value, well, 7/4. But what does it say? It says the stock's value in millions. Get used to this. In calculus, you'll see that a lot. They'll give you a problem where the y value can be measured for thousands. So your answer is 4. Well, the answer is really 4,000. Here the answer is 1.75, so it's 1.75 million, which is 1,750,000. That make sense? But still, what are you looking at? The ratio of the constants. Okay, the ratio of the constants. For the next one, don't scroll down yet. Take a look at this next one here. What's the y-intercept? Don't scroll down, please. I know you can. What's the y-intercept for this next one?
yeah, define.
Y.
Because there's no constant on the denominator, so with 2x, and you substitute 0 for x, it would just be 0. So it'd be negative 10 over 0.
Negative 10 over 0 is undefined, right? Plug in a 0 here. Well, what's the constant? The constant is really 0. So the ratio of the constant is negative 10 over 0. So what's happening then? Don't look at it. Okay? There's no y-intercept here. What does that mean? The graph will not what? You helped us at the beginning. Now, you started us off. If there's no y-intercept, the graph will not go through
The origin?
the y-axis. It will not cross the y-axis. So what do you think the y-axis is?
Could I be an asteroid or a hole?
Very good. Either one. It could be a vertical asymptote or a hole. It's most likely discontinuity. I can tell you right now that it is a vertical asymptote. Why? Why is it not a hole?
Because the factors don't cancel.
Correct. Remember, for a hole, you need factors to cancel. The factor in the bottom that screws this problem up is x. There's no x that we can factor out of the top. The top can be factored into x minus 5x plus 2, but x minus 5x plus 2 does not cancel with this x in the bottom, which is a factor itself. So this is not an example of a hole. It must be a vertical asymptote. When there's a vertical asymptote on the y-axis, it's the line x equals 0. Again, what would cause the denominator to become 0? Remember, I set the denominator to 0, which is this. So this is your vertical asymptote. If that occurs, well, as a result, you cannot have a y-intercept. Okay? Now, for number 3, let's take a look at the x-intercepts. I want to find the x-intercept of this. We haven't done one of these yet. I want to find the x-intercept. To find the x-intercept, what do?
You said y equals 0.
Set y equals 0. Let's do that over here. Oops, minus 5. Now, the question that is difficult for a lot of students to understand is this. Why is it only the numerator that matters? Why doesn't the denominator matter? I want to find the x-intercepts. Remember, x-intercepts are like the roots of an equation. Why doesn't the denominator matter?
As long as the numerator is 0, then it's 0.
That's exactly right. What is a fraction of 0 defined as? 0 over some number. What's 0 divided by 5? 0 divided by 2. Right? Over and over. So all that matters is that the numerator is 0. So define the roots, set the numerator equal to 0. Okay? Set the numerator equal to 0. Some math teachers will teach students multiply by 2x on both sides. Well, 2x times 0 is still 0. And that's a good way to think about it. But reasoning-wise, I want you to think about the fact that it's the numerator that causes a 0 for a fraction. The denominator causes the fraction to be undefined if it's 0. So the numerator gives us the x-intercepts. The denominator gave us either the vertical asymptote or the holes. So we're going to put all these pieces together. Do you see how they're kind of related now? So to find the zeros of a function, or the x-intercepts, or the roots of a rational equation, only look at the factors of the numerator. Now, if a factor in the numerator appears in the denominator, it's clearly what again? What's the word for that? There's a factor on the top and the bottom. What's there? What is it? A hole. If there's a hole, it can't be an x-intercept. Again, if x plus 2 was in the bottom also, x plus 2 would cancel, and x equals negative 2 would be where a hole is. You cannot have an x-intercept where a hole is, because a hole is an open circle. It would be an open circle on the x-axis. Okay? Actually, would it be? Hold on. No, we're not. We're not. This is not an x-intercept. Okay? It's not on the x-axis. Let's look at an example of that now. I think that's what the next one is. Yeah, perfect. Okay? So let's take a look at this one. Now, this is a physics and calculus example, but this topic is very easy, so I'm trying to come up with ways to make it a little bit more difficult for you. So you have to think outside the box. So a particle's motion is represented by the velocity function given there, in meters per second. Determine when the particle is at rest. What does it mean to be at rest?
Yeah, velocity.
No velocity, not moving. So what should I do to the velocity function?
Set to 0.
Set it to 0. If I set a function to 0, I'm finding the x-intercepts. In this case, it's t I'm finding. But remember a moment ago I told you, t is always on the horizontal axis. So the x-intercepts in this case are what we're finding, also known as the t-intercepts. Doesn't matter really. So set it equal to 0. Factor. Cancel the holes. T minus 3 is equal to 0, so the particles at rest at t equals 3. Now, t minus 2 is clearly a hole. Let's see what this would look like on a graph. Here's my x-intercept at 3. What would the y-intercept be here? What would the y-intercept be? Come on, ratio of the constants, quick. What is it? Y-intercept, guys. Ratio of the constants, guys. Negative 3. So I already know that the graph's going to be something like this. It's probably going to be curled. You know how to keep curling these graphs? We'll see that in the next section, but just to see a preview. Now, when t equals 2, how do I find out the y-coordinate of that hole? Think back. Think back.
You substitute your condensed equation.
Simplified equation, yes. The simplified equation is extremely simple here, isn't it? It's just what? Yeah, it's just a linear function, actually. So in this case, the velocity function is not curved. It's a linear function. If you graph this, you're going to see it's a linear function with a hole at t equals 2. So really all I have to do is this. Ready? Connect these dots. And there's a hole here. And I'm 100% sure it's a linear function because the simplified form is linear. Look at it. T minus 3. There's the simplified form. That's what this is. If I want to figure out that actual y value, take the 2 and plug it in. What's 2 minus 3? Is negative 1. Again, guys, take the 2 here, ready? Plug it into the simplified form. 2 minus 3 is negative 1. That goes in here as the y-coordinate. So this coordinate here is 2 comma negative 1. This is 3, 0. And this is negative 3. I'm sorry, 0, negative 3. Okay, again, this function shows a particle that is moving to the left, but slowing down, slowing down, slowing down until the velocity is? And then the velocity becomes positive, doesn't it? So then what happens? Starts moving this way then. Okay, velocity, you're going to learn in physics, is a vector function. A negative velocity means motion left or down. Positive means right or up. So that's what's physically happening. Look, in the beginning of time, what's my velocity? -3. So it's like a runner running this way at -3 meters every second. That's pretty darn fast. How big is a meter? It's like a full step. Every second you're taking 3 steps. So imagine sprinting. You could probably get 3 long steps in when you're sprinting. So I'm starting sprinting. I'm not going to sprint. Sorry. I'm sprinting. And then I slow down, I slow down, I slow down. And then I stop. That's the x-intercept right here. Then the velocity becomes positive. So I start to do this. Move this way. Okay? Does that make sense? You're going to have these problems in calculus. I'm trying to give you a little preview. So when you get to AP calculus, the line is a lot easier for you. If you understand the concepts now, and then later on, what we have to go over is the calculus involved. You're going to do this with calculus. You're going to solve these problems with the techniques you learn, but they're literally the same setup. Okay? So we're taking a little preview of what you're going to see. How about number 5 here? What are the zeros of this rational function? What are the zeros? What do you notice in this one? Take a minute, maybe look at it, and then somebody describe this a little bit, please. Again, we're looking at number 5. Hold off on number 6. Take about a minute, and I'll ask for some hands to hear about it. You know what I forgot to do this year, I did last year? I should have done a flipped classroom some days. I did that last year when I have students, you know, I have videos I post, I watch them for homework, and then come in and we do problems over here. I never did that. It's still in my mind. So what do we have here? What do we notice happens? In the numerator right away, you take out what? What is it called here? X, which is called what? What's the term for the thing you take out? It's going to be a zero function, but it's the greatest common factor. Start with taking out your GCF. Factor the remaining quadratic, which was x squared plus 6x minus 27. What happens next? Now, what happens next after we get all those factors?
X minus 3, x minus 3 cancels.
So that's a
whole.
good. So x equals 3 is clearly a whole. X equals 3 is a whole. Leaving behind x times the quantity x plus 9. Kelly? What's the last part? So we have x and x minus 9. Or x plus 9 rather?
You're just like, z equals 0.
Yeah. So in this case, we have x equal to 0 as one of our zeros. That's one that a lot of people forget about. That's the only reason I make this problem this way. I don't know why it is. If you take out a GCF and it's one of your factors, please don't forget to write it out as one of your zeros. Okay? X equals 0 and x equals -9. Alright, so that's our conclusion from this lesson today. Alright, right here. That's the main conclusion that we gained. So, number 6, try as like a challenge problem. Don't look at the actual solution yet. Try and figure out number 6. Spend you have about 10 minutes. Try to factor that numerator. How could you factor that numerator? What's one way to try and figure out how to factor that numerator? You could try by grouping, sure. If grouping works, do that, yeah. What else could you do? Aside from grouping. Mike?
Use division.
Yeah. You can use synthetic division. You could try numbers. Remember how we used Descartes' rule of signs? The rational root theorem? P's over Q's to come up with the roots? Well, the roots, remember, are the opposites of the factors. So if you can figure out the roots of this one, a numerator, say one of the roots is 1. We're going to try 1, it works. That means x minus 1 is a factor. If negative 7 works, x plus 7 is a factor. So try and figure out the factors of the numerator by using rational root theorem and Descartes' rule of signs. Try and factor it. The denominator is very easy to factor because the GCF can be taken out, and then you're going to have to use AC method. Okay, so spend about 5-10 minutes in this problem, try to figure out what it is. And when you do, scroll down and check the factors that I have there. See if the factors are the same ones you got. So this is going back to chapter 8, where we did rational root theorem and Descartes' rules. This would be like a very difficult problem, but definitely a problem for like a final exam that covers more than one topic. So you have to use rational root theorem and Descartes' rules, and you'll also have to use rational function ideas here. This would definitely be calculus, pre-calculus level problem. By the way, what's the y-intercept? This one's easy. What's the y-intercept? What? There is no y-intercept, right? Remember, no constant in the end here? Y-intercept. It's definitely a vertical asymptote or a hole on the location x equals 0. If you're struggling with the synthetic table, please call me over. This is the time for me to help you with it. So once you get your first root, you want to make a subtable. Then make another subtable. So the goal here is to figure out the roots of the numerator so we can find its factors. So look at the numerator first. Look at the possible roots. What are the possible p's over q? What are the possible factors of 30? 31, 65, 215, 310. This is a lot, right? So what I would do is I would make a synthetic table first. Okay? To make the headings whatever the numerator's coefficients are. Which are going to be 1, negative 1, negative 19, 49, and negative 3. Now, what's the easiest number to test on this? 1. Okay? Start with 1. Remember, this is going to be a running table. I'm going to keep trying numbers below. Check each other, see what the remaining is right. You're at 0? So something in the state. What? sure? What's the other thing? Sorry. Good. 1, 0.
Yeah.
Sure?
That's got it.
Alright, so if one of them is 0, look at the resulting equation that's in that line. So that's why I had you look for it. See the 1, 0, negative 19? See that? That's your next table. So make a new table now. Look those as your headings. It's called the subtable. So now notice this. The depressed equation. Very good. Yep. And notice on top you have the other 4 numbers. In the previous one, there were 5, because you're going down by degree every term. So now in this table, you try one again, because it could be a double root. But really, you should try one to start. I'll try one first. Don't erase the one. Yeah, no, keep going. That's what I said. So running table. Write that line down and go to the next column. 2 does work for you? Does 2 work for you? Just try 2? Now, what I wanted to look at now is what are your numbers across for 1? What are your numbers across? 1, 1, negative 18, 12. What's your name? 1 times 1 is 1, plus 0 is 1. 1 times 1 is 1, plus negative 19 is negative 18. Alright, so look at the numbers across. There are no alternating signs, so it's not a lower down, and we didn't try negative numbers or numbers. There's none of the same signs, it's not up and down. So at this point, in one direction to choose. That's why I was doing 2 minutes, just so that it's constant number. And now remember, my P's or Q's, it's still the same P's or Q's as one of them. I've got the new depressed equation you're looking at, even though it's still 30 on there. When you try 2, tell me what you get across. Good. Brad, agree? So 1, 2, negative 15 is your next depressed equation. But isn't that quadratic at this point? So make it 1x squared, write this down, 1x squared, we'll leave the 1 plus 2x times 15. That's the next equation. Now just solve either factoring or quadratic formula. You use the program like this is factoring. What's the factoring? Sorry, you said, well, the roots are later. Yeah, so the factors. Now remember, your goal was to factor the numerator. So these are junior factors, aren't they? The other factors come from the root you got that worked. Didn't 2 work as a root? So isn't x minus 2 a factor? And didn't 1 work? Did 1 work actually? Yeah. So x minus 1 is a factor. So scroll down the notes now. Look at the factors after that. Add those 4 factors, the one thing you just told me? Okay? So any of those cancel with the denominator's factors. The denominator, you would factor out x. You see that? And then you would factor that by using AC method. It's a GCF and you have x. Take x out and then use AC method. But none of those factors cancel. So there's no holes in this graph. All 4 numerator factors turn out to be x-intercepts. So there's 4 x-intercepts here. 4 that you got. 1, 2, what is it, -5 and 3. The opposites of the factors. Thumbs up, down, right? Yeah?
Were we supposed to submit that you want to do homework?
Yeah, please do that, Gavin.
Thank you.
You're welcome, guys. All right, there's 2 pages of homework for this tonight. Or this weekend, I guess, right? So you could start 5-9 this weekend, those 2 problems I told you about, and then take it all together.